In this video, I will present formulas for the derivatives of the 6 trigonometric functions. I will explain how to prove them quickly and how we came up with them in the first place. First, as a summary, here are the 6 derivatives. The derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is minus cosecant cotangent. Notice that the second column can be obtained from the first column by adding minus signs and swapping sine for cosine, tangent for cotangent, and secant for cosecant. I advise that you memorize the first three, sine, cosine, and tangent, because you will use them a lot. As for the rest, if you ever need them and you do not remember them, they take 20 seconds to derive, as I will explain later. I need to prove these 6 identities, but I am lazy. I do not want to do all 6 from scratch. Instead, I will use an old-time tradition in mathematics. Do the hard work only once and then milk it for all it's worth. Yes, I'm going to have to prove at least one of the 6 the long way, from the definition of derivative as a limit, but after that, I can use the many relations between trig functions to reduce the other 5 to the one I have already proven. Here's what I mean. First, I need to obtain the derivative of sine from the definition of derivative. Second, we can write cosine as the composition of sine and a polynomial. Then, if we already know the derivative of sine, we can simply use chain rule to get the derivative of cosine. Finally, the other 4 trig functions can all be written in terms of sine and cosine. For example, tangent is sine over cosine, secant is 1 over cosine, and so on. Once we know the derivative of sine and cosine, we simply use the quotient rule. And that's it. This plan is entirely rigorous, and it is much simpler than proving all 6 of them from the definition. I will leave steps 2 and 3 as exercises. They are pretty quick calculations. It is worth doing them once. If at a later date you need the derivative of cosecant, for example, and you don't remember it, you can simply repeat the derivation. It takes 20 seconds. Now I will show how to do step 1, which is the hard part. First, I will use the definition of derivative as a limit. X and h are mixed in here. I can separate them with a trig identity. Sine of x plus h equals sine x cos h plus cos x sine h. And I'll keep the rest as is. Now, for the purpose of the limit, the variable is h. So x is kind of a constant for the purpose of the limit. And sine x and cos x can also be treated as constants for the purpose of the limit. They do not depend on h. I'm going to separate the pieces that depend on h from the pieces that do not depend on h. And now I am thinking of this expression as a number times a function of h plus a number times another function of h. So I can use the limit laws. Of course, I can only do this if I know that this limit exists and that this limit exists. But I got lucky, because these 2 limits are limits I already know. In an earlier video, which I will link in the description, I already computed these 2 limits, and I computed them from scratch, using only geometry and trigonometry, nothing more. And I learned that this limit here is 1, and this limit here is 0. So, the derivative is going to be sine of x times 0 plus cosine of x times 1. Or in other words, simply cosine of x, which is what I wanted to show. To conclude this video, for any fans of using L'Hopital's rule to compute every limit, I have a warning. If you don't know what L'Hopital's rule is, don't worry, ignore this final part of the video. In the video I have linked, I proved that the limit as h approaches 0 of sine of h over h was 1. Perhaps you thought the proof I used in that video was unnecessarily complicated and long. After all, why not simply use L'Hopital's rule to compute this limit? Well, in order to use L'Hopital's rule to compute this limit, I need to already know that the derivative of sine is cosine. But as you saw in this video, in order to prove the derivative of sine is cosine, I need to already know that this limit is 1. And this looks like a cyclic argument. That is why it was very important to prove that this limit was 1 using only elementary methods, only geometry and trigonometry, and not L'Hopital's rule. Because otherwise, we would never be able to conclude that the derivative of sine was cosine, and then we would never be able to use L'Hopital's rule in the first place.